Okay, so we've been learning about solving differential equations. So now it's a good time to see some application. And we're looking at a type of problem that's about springs. So the situation is that you hang a spring kind of vertically, and then you can hang an object onto the spring that will have a mass 0, and we assume there is no like mass for the spring, so there's only the mass for the object. And then what you can do to it is you can either push it up or pull it down by a certain distance, and then from that point you release it freely. And you can imagine that with a spring it will kind of oscillate up and down, and if we assume there is no kind of loss of energy or like resistance, then it should oscillate up and down forever with the same amplitude. So we want to describe that kind of theoretical like motion at all times, since we assume it will kind of oscillate forever. So you can imagine, because if we think of oscillation, we will immediately think of the sine cosine function. And it turns out that it will be, the movement will be a sine cosine function. And then we also want to kind of sketch the solution y of t, and also we want to compute the period, because the period doesn't have to be like 2 pi. It can change. So an application problem, usually it will look very long and kind of intimidating, but let's just kind of analyze it line by line. So this is a spring problem, and then let's just kind of look at it line by line. So the first line, it says 1 kilogram block hangs on the spring. So it just says the mass is 1. And since we're if you're using kind of standard units like G, instead of say like pounds, then you don't have to kind of always keep track. So that's the mass. And then the second line, spring constant. So there's nothing to it. So this constant is an intrinsic thing for a spring. So you can imagine if I get a different spring with maybe made of different metal, then the constant will change. And then the next line, the block is pulled down. So there is something important in this line. It's first of all, it tells you kind of the initial displacement, right? Initial position. So it's 0.75 meters. But it's very important that you know why this one is kind of defined to be the positive. So this is kind of I think it's just by definition we assign like one direction to be positive or negative. That's how to kind of be consistent with the formula and all that. So whenever it says like the spring is like pulled, like maybe make sense of the positive sign as if you pull it down, it's longer, right? So then it makes sense, it's like a positive. And if it's push, if it's like pushed to by a certain distance, then you should interpret that as like a negative number, even though in the statement it probably won't put a negative sign, but you should know one side is positive, the other side is negative. So next, released with no initial velocity. We know that velocity is the first derivative of distance. So initial means time equals 0. So that just means y prime of 0 is 0. And then the next line doesn't really say much. It just explains why it will kind of oscillate forever. Because usually we will expect the spring to like eventually stop. But if you make this like theoretical assumption, then it will oscillate up and down forever. And then we want to find a position at all times. So the goal is to find y of t. And then we also want to do a graph and compute the period, because the period doesn't have to be 2 pi. it can change if you put some like kind of coefficient inside the sine cosine. So I think in the lecture we've talked about, you should take a look at the lecture notes. We kind of derived this formula, and it's really like not hard. I mean, the only thing that's like intimidating is instead of like a number, it's like a square root of these like letters, symbols. That's what makes it look very hard. But if you think about it, if you just think about K and M as like constants in the derivation, it's really like a very standard thing. And I guess, I already listed all the values you need. So it will be C1 sine square root of 1.44 is 1.2. So this is also 1.2t. So I guess at this point, if you write down this general solution and you have these two things, it's kind of easy to compute what's C1 and C2. So I think I'm just gonna copy the answer, so we can compute that. Right? You just take derivative once and plug in the 0, and you'll be able to get C1 and C2. So I'll just write, can compute C1 is equal to 0, C2 is equal to 0.75. So that's done. So maybe we want to kind of write one more line to make a conclusion. So YT is just equal to C2 is 0.75 cosine 1.2t, right? So as promised, it will be a sine cosine function. And even though, maybe it's hard to believe at this point, but even though, even in the situation that both C1 and C2 are non-zero, right? It looks like it's a sine and a cosine. You can still write like a sine cosine like this as just one sine or cosine. I think it's also in the lecture notes. So kind of be careful with that. So that's kind of the solution for this initial value problem. And then we just want to do a graph and compute its period. So you can imagine that this thing will certainly be related to cosine t, right? You just need to maybe scale it a little bit, maybe scale the amplitude, and also kind of rescale the like horizontally, which means the period will also change. So how do we compute the period? So the formula to compute the period is 2 pi over omega, and omega is this coefficient here. Right, so in our case, it's 2 pi divided by 1.2, which is 20 over pi over 12. So that's divided by 4, that's 5 pi over 3. So that's our period. Instead of 2 pi, now by putting a coefficient here, you change the period from 2 pi to 5 pi over 3. And this is the formula for computing the period. So how do you graph it? I suggest you do not put the kind of the grid first. You draw the kind of the function first, and then you mark the values. That will be easier. Otherwise, if you just kind of already marked the values, then it's really hard to kind of you have to be very careful when you kind of trace along to make sure the scale is correct. So I suggest you do the sketch first. So since it's some kind of a cosine function, we know cosine function will look something like this, right? So maybe do like 2 periods is enough. And now we need to label something. First, it's a function with respect to t, and then we know the period. So what is a period on the graph? So this is a full period, right? Until here, it's a full period. So that means it's from 0, so this point should be 5 pi over 3. And if you want to be like more careful, this should be half of that, so 5 pi over 6 is what it is here. And you also want to label the amplitude. So the amplitude is the coefficient here. So without the amplitude is 1, right? And that's the 1 here. So with the amplitude, it is now 0.75. That's the new amplitude. So that's a sketch for the solution.